All right, next up is problem number 3 that says consider the thin plate bounded by the parabola y equals x squared and the line y equals 9, whose mass density measured in kilograms per square centimeter at a point xy on the plate is given by rho of xy equals x squared plus y. Assume the distances are measured in centimeters. So part A is asking us to find the mass of the plate, being sure to include units in our answer. And so up here, I've gone ahead and included a figure of the plate. So we have the parabola y equals x squared and this horizontal line y equals 9. And notice those will intersect when x is 3 and negative 3. And so for the mass calculation, well, we're just going to integrate this density function over our region R. And that's a pretty straightforward calculation here. Now notice I'm going to fill out this region with vertical strips here. So for a fixed x, y will vary from x squared to 9. So this will be a dy dx integral, again, where y goes from x squared to 9, and x then will range from negative 3 to 3. So we're filling out this region R with vertical strips as x varies from negative 3 to 3. Now you go ahead and do that calculation, and you wind up getting 1,296 divided by 5. And as far as the units go, well, our density is in kilograms per square centimeter, and our little change in area then, since distances are measured in centimeters, the change in area will be in square centimeters, so this product will have units of just kilograms, as it should, because kilograms is a unit of mass. All right, so then for part B, it says find the center of mass of the plate, making an appeal to symmetry where appropriate. Okay, so notice here, by the fact that this plate is symmetric with respect to the y-axis and our density function rho is even with respect to the y-axis. Okay, so in other words, if I take a point over here in quadrant 1 and then I reflect it about the y-axis, okay, since we have this square on our density function for x, the density at this point in the first quadrant will be the same as the density over here in the second quadrant. Okay, so if I'm thinking about now, right, say the rotational tendency of our plate about the y-axis, well, there won't be any rotational tendency. There's essentially a cancellation of effects. Think about the seesaw effect across the y-axis here. And so all that together is going to tell us what? It's going to tell us that that y moment is 0, okay, by this appeal to symmetry, and the x-coordinate then in turn of our center of mass will lie on the y-axis. Okay, so that's nice. It just allows you to dodge a integral calculation. All right, so now for the x moment, well, we actually do have to do a calculation there. So we're going to integrate y times the density function. And again, we'll just use these vertical strips. So we're going to integrate y times the quantity x squared plus y as we let y vary from x squared to 9 and x is varying from negative 3 to 3. Go ahead and run through that calculation. You wind up getting 11,664 divided by 7. All right, so then the y coordinate of our center of mass, so y bar, would just be that x moment divided by the mass. So we're going to take the 11,664 divided by 7 and divide all of that by 1,296 divided by 5, right? That was the mass we computed up here. And we get the coordinate 45 sevenths, which is about 6.429. Okay, so looking here at our region, at the very bottom, y is 0, and at the top up here, y is 9. And so our y coordinate for the center of mass is going to be, roughly 6.5. Okay, so that does make sense given the fact that if you look at your density function, okay, if I fix an x, letting y increase, our density will increase. So it would make sense that we're going to be looking at a center of mass sort of towards this higher end here. All right, cool. And then putting that all together, we can say that the center of mass is located at the point 0, 45 sevenths. Okay, part C says, suppose now that the mass density is given by this new density function, delta, and delta xy is equal to x plus 3, it says, without performing a calculation, in which quadrant will the center of mass lie? Explain. All right, well, Now I do not have this symmetry going on with my density function. Okay, so if I think about what this density will imply about the distribution of mass for my plate, well, if notice that this is independent of y, so if I imagine moving along a horizontal strip, okay, the density is just going to increase linearly with x. So I'm going to be a lot more dense here in quadrant one. So as you move to the right, you're going to get more dense. As you move to the left, you're going to get less dense. Okay, and so from that observation, our center of mass now is going to lie over here in the first quadrant. Okay, so again, we lose that symmetry just because our density now is not symmetric with respect to the y-axis, but nonetheless, we can at least conclude that it's going to lie somewhere in the first quadrant. All right, that's going to do it. Thanks.